Okay, so just for fun, let's discuss the binomial series real quick. If you flip to L.3, this just shows up. Wow, okay. So for starters, as I'm reading through this, I realize, I actually had to do the last exercise from L.2 in order to figure out anything. And in fact, the general result is this monstrosity, which, what the hell does that mean? Oh, and the rest of the proof is actually later on in the book in section P, so that's super helpful. What is going on here? And why is it called the binomial series? Well, I do see right here that we have a binomial expansion happening. And we talked about that back in chapter 8. If that p, the exponent there, happened to be 0 or a positive integer, then I know what 1 plus x to the power of p is. It's equal to that expression. Usually we see it with another term right here, but that's just going to be 1 to the power of n minus 1, so that's just 1, so that's why we're not writing it. Here now we're going to generalize this. Find out what would happen if p was not a positive integer. What would happen if it was just some rational number? What if it was negative? Oh my gosh. So we can work this out. Now your book just gives you this thing in the blue box. What the hell are you supposed to do with that? Let's actually derive this. Okay, let's go through it step by step. So this is from another book, and we've changed the p to a k, but otherwise it should be no problem. So we've got this function. We're going to come up with a power series for it, a Maclaurin series, in fact. Well, that means we're going to take a bunch of derivatives. That's easy to do, right? We're just using the power rule for taking derivatives. And we see a pattern emerging here. All right, so we're getting like a k factorial coefficient is showing up. And on the right-hand side, we're just evaluating each of these expressions for x equals 0. And we see another pattern happening here. It's actually the same exact product on every level. So therefore, we have an expression for the general nth derivative. And from there, we can work out that nth derivative evaluated at x equals 0. And then that becomes our coefficient. Since this is a Maclaurin series, we start off with f of 0, which is 1, plus x times f prime of 0, so that's kx, plus x squared over 2 factorial times that, which we've got here, and so on and so on and so on. In general, we will have x to the n divided by n factorial multiplied by that term. And this you may recognize from here. So that's where that all came from. What I like about building it term by term is that written out as this series, this actually makes sense now for even positive integer values for k. So for example, if I wanted to work out what 1 plus x squared is, okay, I know that's supposed to be 1 plus 2x plus x squared, right, obviously. But that actually shows up directly from here. Because if I set my k value to 2, I get 1 plus 2x plus 2 divided by 2 times x squared. So this is actually a new way to calculate binomial coefficients. Oh my gosh. It's not obvious how to come up with 1 plus 2x plus x squared from this thing, because when we just see this product, clearly for any positive integer, that's going to become 0. Right? Because my first few terms here are p times p minus 1 times p minus 2 is next, and if I set p equal to 2, well then I've just multiplied by 0. So that kind of gets a little bit weird. But if we derive it, then we can work with the binomial series no problem. Here's one example of it. So finding the power series for this function. Well, we can rewrite that, right, as 1 plus x to the power of 1/3. We've just worked out this sum on the previous page, so now we just set k equal to 1/3, and here's our series. To work it out with a giant formula, we would just have to work out kind of a few various terms for n one at a time. It's not obvious from the way this is written out what the coefficient should be. So shortcut, when n is equal to 0, it's just going to be 1 like every time. And that's because any binomial expansion of 1 plus x, it has to have 1 as a constant term. So we're just going to say that always happens when n is equal to 0. And we can see that's going to be 1, that's going to be 1. But what's happening with the rest of this stuff? If n is 0, I've got like 1/3 times 1/3 minus 1 times 1/3 minus 2. These terms are getting smaller and smaller and smaller. Oh, except here, when n is 0, all of a sudden it's bigger. Now it's 1/3 plus 1. That doesn't make any sense. It hurts my head. So we're just going to say when n is 0, it comes out to be 1, and move on with our lives. Now, recall from over here, if we look at what the coefficient of x is, we can figure out kind of what coefficient comes in front of it. So look, when x was 1, we got just k. When x was to the power of 2, we've got k minus 1. When x is to the power of 3, we're going to have up to k minus 2, and so on. So here, when n is 1, we're going to have only that first factor. So this is going to be 1/3 times x to the power of 1 divided by 1 factorial. That's just 1/3 of x. When n is 2, we're going to have, well, obviously, x squared. And then we'll have 1/3 times 1/3 minus 1. So 1/3 minus 3/3, that's negative 2/3. 1/3 times negative 2/3, that's going to be negative 2/9. But then we're dividing this by 2 factorial, which is number 2. So it looks like negative 2/18 times x squared. We'll just take a look here. That's exactly what we got there, if you evaluate that. And the rest of the terms are going to be the same as well. So you can work this out using the formula that the book gives us, but I don't know, like this formula is not in the formula book, so I don't really feel like memorizing it for a problem that the IB has never asked about. Do you? I don't think it's worth it. If I had to do an expansion of this kind, I would just do it the old-fashioned way. I'd take derivatives, I'd evaluate at 0, and I'd come up with the series like that. It'll be fine. Anyway, that's it for this topic. I don't want to go into a lot of depth in it because, as I've said in like all 3 of the previous videos, the IB's never asked a question about it. I don't see the phrase binomial series anywhere in the syllabus, so I don't think it's necessary. But it is kind of neat though, because getting this new way to come up with binomial expansion, that explains why on a calculator, if we were to ask it, hey, what's 1/2 choose 5? Calculator gives us an answer for that. But like previously, we only thought about choosing in terms of positive integer values. Like that's like if I have 1/2 of an object, how many ways can I choose 5 of them? That doesn't make any sense. And for integer values, like if I change that 1/2 to a 1, it's going to be 0, right? There's 0 ways that I can choose 5 out of one object. But if I make it a fraction, all of a sudden it has a value to it. So yeah, there's like a whole wide world out there of like further combinatoric stuff you can do with non-positive integers, and I don't know, it's pretty wacky, but there it is. It's kind of connected to this calculus series topic. Okay, enjoy studying. Bye-bye.